This is video 46 in our series on tensor calculus. In this video, we'll discover that tensors are really a subset of a larger class of objects known as relative tensors. We ended the last video with the expression you see here. This tells us that our newly defined delta function is the equivalent of the product of our permutation symbols when they're combined like this. Now, this lets us modify our expression for the determinant to look like this, obviously much more concise. Now, we've said all along that we were just working with a system of numbers here, that Aij was not necessarily a tensor. It's just a system of numbers, a two-dimensional matrix, and we could have written it with indexes in the upper position, lower position, or mixed as they are here. But now, let's suppose we know for a fact that Aij is a tensor. Let's say this is a known second-rank mixed tensor. Well, the other advantage of the form that we've expressed our determinant in here is this. If Aij is a tensor, then this is a tensor, so is this. And we learned in the last video that our new delta function is also a tensor. Now, because that's true, then the product here is going to be a tensor, and that means that A itself is a tensor. And of course, since we have a full contraction, it is a scalar function. So we can say this, that the determinant of a second-rank mixed tensor is a scalar function, or a tensor. Now, a very handy form to express this in is as follows. We would say that A with a dot in the upper position, lower position, with prime symbols written inside the vertical bars is equal to A with two dots inside the vertical bars. So what this is telling us is that a determinant of a second-rank mixed tensor in the Z prime system is equal to the determinant of the second-rank mixed tensor in the unprimed system. So this form gives us all that information. Now, we don't use actual values for our indexes here, I and j, because these things don't represent free indexes or contractions anymore. This whole expression represents a determinant, and we're just saying that we applied our rules for the determinant to an expression that had an upper index and a lower index. All right. Let's use our syntax now to derive a very important relationship regarding determinants. Let's say that we knew that our tensor Aij is actually equal to a contraction of two other mixed rank tensors, Bik and Ckj, and we're contracting them here with this dummy index of k. So let's see where this leads us. Well, I'm going to substitute this expression into the one we have for our determinant. So we'd have A is equal to 1 over 3 factorial, and I'm going to expand these terms out. It's E R S T times E ijk, and instead of writing AIR, I'm going to write I'm going to write B with an upper index of I and C with a lower index of R, and I need a new letter here. I'll use M for the contraction. So BIMCMR is the same as AIR. I'll do the same thing for the other factors. So AJS is going to be BJ, and it'll have a C with a lower index of S. We'll use N as our dummy index here. And the final term is BK with CT, and I'll use, I guess, a P here. All right, now I'm going to reorganize the terms a little bit. I'm going to take the, let's say, this EIJK factor with all of the factors of our B tensor, BIM, bjn and bkp. So we'll group all of those together, and we'll put everything else together in a group. 1 over 3 factorial times ERST, and all the remaining factors of C, which will be C, MR, CNS, and CPT. Okay, now if you go back a couple of videos, you'll remember that the expression you see right here can be written in this form. This is just equal to our determinant B times E M N P. So these two are the exact equivalent of each other. And you'll find this, I think, 2 videos ago. Okay, so now we'll just copy the rest of it over here. 1 over 3 factorial E RST CMR CNS CPT. Okay, now by inspection here, I think you can see that if we took this factor and combined it right over here, then this expression, if we combine this with this, we're going to get our delta function like this. And altogether, this expression inside the parentheses is just equal to the determinant C. In other words, we've now derived the fact that A equals B times C. What this means is if we find the determinant of B to get this, and then the determinant of C to get this, and then multiply the two results together, we'll get the same result if we just find the determinant of A in the first place. We say that the product of the determinants is equal to the determinant of the product. Now, this important property is not limited to tensors. It's true for determinants in general, but it is in no way intuitively obvious. Now, the simple proof you see here is a great example of the power and utility of tensor calculus. It's extremely difficult to prove by any other means, such as linear algebra. Okay, we'll make use of this in a few minutes, but for now let's go back to our main line of investigation. We've determined that the determinant of a second-rank mixed tensor is a tensor itself. But what about tensors with 2 upper indexes or 2 lower indexes? Well, we can't use this approach because we can't apply this delta function in that case. This delta function only works for expressions that have an upper index and a lower index. So we've got some more work to do to see if this principle applies in those cases. So here we have the expression for the determinant of components that have 2 lower indexes. So if we know that Aij is a tensor, then of course we know that each of these factors are tensors, and so the product will be a tensor. So the question of whether A itself, the determinant, is a tensor boils down to whether the permutation symbols themselves are tensors. So to answer the question, we've got to find out what the transformation rule is for our permutation symbols. So let's start by assuming that Eijk is a tensor. Well, if that's true, then this would be the case. Ei prime j prime k prime would equal Eijk times each of the Jacobian factors needed to transform as a tensor. So we'd need j I prime I, j prime j, and j k prime k. So this is what we'd have to see if in fact Eijk transforms as a tensor. But we can see immediately that that is not the case. It can't be true because if you look back 2 videos ago, we saw an expression like this where we took a form that had an upper index, a lower index like this, multiplied the 3 together times eijk, and we discovered that that's equal to the determinant of this system times this factor. In other words, what we know to be true is that this expression on the right is equal to e I prime, j prime, k prime times the determinant of j, and I'll use the symbol we talked about before, that this is equal to the determinant of j represented in this form. It is the determinant of a system that has a prime index on the top and an unprimed index on the bottom. So because this factor shows up, we know that eijk is not a tensor. All right, but let's see if we can clean this up just a little bit. Now we know that the Jacobian I prime contracted with the Jacobian j I prime j like this is just going to produce a Kronecker delta ij. So now if we were to find the Jacobian of each of these factors individually, then this first factor would be the Jacobian with a dot and a dot here and a prime symbol on the bottom. This would be the Jacobian with the dot and the prime symbol on the top like this. Now what's the determinant of the Kronecker delta? Well, that's just equal to 1. Now we know this expression is true because of the property we derived just a few minutes ago. The product of the determinants is equal to the determinant of the product. So the product of these two scalar values is equal to this scalar value because we can take the determinants individually as factors. So it boils down to the fact that these two expressions are reciprocals of each other. All right, so for convenience, let's say that the first one, j with a dot and a dot prime symbol, is just going to be equal to j. And that means that j with the prime symbol in the upper position is going to be equal to the inverse, which is j to the negative first power, like that. So now we can write our transformation rule for eijk this way. Now all I've done here is, this guy over here, this j with the prime symbol on the top is equal to j to the negative 1. So I just multiplied both sides by j, and this is what we get. So now let's do the same thing for eijk in the lower position. So if we had e with I prime, j prime, k prime in the lower position like this, it would be equal to eijk with Jacobian factors with the indexes reversed with I prime, this is a prime, and j prime, and j, k prime, and that expression would be true if we added a factor with the prime symbol on the bottom down here like this. Okay, that in turn leads us to the transformation rule for this particular form. And again, we see that this is not a tensor because we get this extra term right here. Now, even though these objects do not transform as the tensors we've been working with, they are examples of what we call relative tensors. Now, a relative tensor is an object like this that transforms with the usual Jacobian factors, just like a normal tensor, but also has this additional factor of the Jacobian out here. And we classify these relative tensors according to the exponent. We say that this was an example of a relative tensor of weight 1. This is a relative tensor with a weight of negative 1. So the exponent of the Jacobian factor is known as the weight. All right, so that means that the tensors we've been working with all along are really relative tensors with a weight of 0. It has no Jacobian factors or an exponent of 0. Now, the full name of what we've been working with is what we call an absolute tensor. So an absolute tensor is just a relative tensor with weight 0. Now we'll continue to call them just tensors, but I just wanted you to see what the official name is. So all of these things are tensors. Some of them are relative, some are absolute. We've been working with absolute tensors now for some 40 videos, and it's just now that we're seeing the first case of relative tensors. All right, so now let's take what we've learned about relative tensors to see how this expression transforms. Okay, I expect by now you know the kind of drill we have to go through. We first express the relationship as it looks in the Z-prime system, and then substitute in the transformation rule for each of the factors. So we'll have A prime is equal to 1 over 3 factorial times the transformation rule for E, I prime, J prime, K prime, and that is just J times E, I, J, K times all the Jacobian factors we need. So we'd have J, I prime, I, J, J prime, J, and J, K prime, K. All right, we have to do the same thing for the second factor, which is going to be J times E, R, S, T, and the Jacobian factors are R prime R, J, S prime S, and J, T prime T. Now we need the transformation rules for each factor, and here it's going to be A times, well, I can't use I as an index here because it's already in use, so I'll use a new letter, M times, H? Okay. And then the Jacobian factors of M, I prime, and H, R prime. Now, make sure you see why I can't use I and R here, because I'm using I back here and R over here, so I can't use them again in the same term. Okay, the second one then is going to be A sub, well, we'll use N and I guess F times the Jacobian of N J prime and Jacobian F S prime. And the final term will be A P G, and the Jacobian will be P K prime, yep, and the last factor is the Jacobian G and T prime. Okay, so there you have the expression for the transformation on the right hand side. So let's collect terms and see what else we can figure out here. So A prime, we'll start with this factor of J and this factor of J, so we'll start with J squared. That's this term and this term. Then we have 1 over 3 factorial, and then we'll write the E, I, J, K term right here, and then E, R, S, T here, followed by all of our A factors, A, M, H, and A, N, F, and then A, P, G. Okay, I think that is everything except the Jacobian factors. All right, now let's look at the this Jacobian factor and this one have a dummy index of I prime. So that's going to produce a Kronecker delta of M, I. Okay, now the same sort of thing happens with every one of these. If you look at this one, there's the R prime is a dummy index with this term. So it's going to produce a Kronecker delta of HR. Now this one is going to combine with this guy to produce a Kronecker delta NJ. And this one is going to combine here for a Kronecker delta FS over here. And we have this one which combines here for delta PK. And the last one combines here to give us a delta GT. All right, now all of these Kronecker deltas will absorb the indexes respectively for each of the indexes on our A terms. That'll give us this expression. A prime equals J squared. That's 1 over 3 factorial E IJK E RST times A IR A JS and A KT. And you can see by that that A prime is equal to J squared, and this whole expression is nothing but our determinant for A. So after all of that, we can write it this way. A with 2 primed dots on the bottom inside our bars is equal to J squared times A with 2 dots on the bottom in our bars like this. So we conclude that the determinant of a second-rank tensor with 2 indexes on the bottom that's twice covariant is a relative tensor of weight 2. Now it should be obvious that the expression with 2 indexes in the upper position like this would represent a relative tensor of weight -2. And I'm not going to go through the exercise again. I'll let you do that on your own. But the only thing you have to do here, you go through all these same steps except the transformation rule with EIJK being on the bottom is that we'll have terms with J to the -1 power in 2 positions, and that's why it'll wind up like this. So with that, we'll end the video with a short recap. We started by modifying our expression for the determinant of a system Aij that has 1 upper and 1 lower index. And we did so by replacing the pair of permutation symbols by our new delta function here. Now, aside from making the expression a little more concise, what this does is allow us to prove that if Aij is a tensor, then its determinant is as well. And the reason is that these factors are all tensors, and we know that our delta function is a tensor, so what we have on this side is a tensor product. And since all the indexes are dummy indexes, we have a full contraction, and therefore A is a scalar function. It's the same in all coordinate systems. We then went on to prove a very important property of determinants, known as the multiplication property of determinants. And it simply says this: if we have a system BIK contracted with a system CKJ like this to form AIJ, then the following is true. If we find the determinant of B and the determinant of C and the determinant of the product of these two contracted together, then B times C is equal to A. We say that the product of the determinants is equal to the determinant of the product. And this is a property, a very important property of determinants. That is true in general. It doesn't have to apply simply to tensors. All right, now we then applied this property very specifically to the case of the Jacobian. Now we know that the Jacobian, Ji prime, contracted with the inverse Jacobian, Ji prime j, will give us the Kronecker delta Ij. All right, well, if we now make use of this property, we can tell that the determinant of our Jacobian right here, multiplied by the determinant of our inverse Jacobian here, will give us the determinant of the Kronecker delta. And the determinant of the Kronecker delta is just 1. This is just a special application or special case of the use of the multiplication property of determinants. All right. Well, that tells us that the determinant of the Jacobian and the determinant of the inverse Jacobian are reciprocals of each other. Their product is equal to 1. So if we define the determinant of the Jacobian with the capital letter J, then we can represent the determinant of the inverse Jacobian as j to the minus 1 power. We were then able to derive the transformation rules for our permutation symbols. And we discovered that our permutation symbols are not tensors. And the reason they're not tensors is because of these factors that show up. If these factors were not here, then these would be tensors because they have the necessary Jacobian factors in both cases. But because we see the Jacobian factors, we know they're not tensors. In fact, we discovered that what these are really relative tensors. Now, this one, EIJK with upper indexes, is a relative tensor of weight 1 because of the positive 1 exponent of our J factor. EIJK with lower indexes is a relative tensor of weight negative 1 because of the exponent of negative 1 here. And finally, by substituting these values into our definitions for determinants, we were able to derive these relationships. Now we already knew this relationship. We demonstrated that by use of our delta function, and that is that the determinant of a second rank mixed tensor with one index on top and one on the bottom is in fact a tensor itself, and it's a rank 0 tensor, which means it's an invariant scalar. But if the two indexes are on the bottom, then we find that we don't have a tensor or an invariant expression. Instead, we have a relative tensor. If the two indexes are on the bottom, then the determinant of that tensor is going to be a relative tensor of weight plus 2. Likewise, if the two indexes are on the top in the contravariant position, we're going to wind up with a relative tensor of weight negative 2. So whether or not the determinant of a tensor is itself a tensor depends on the location of the indexes.